Hi, today we're going to talk a little bit about another discrete or countable probability distribution, that is the geometric distribution. I'd like to ask you to take a little stroll down memory lane with me today. Do you remember that game Trouble? That's the one that had the dice built into the board where you had to pop it in the middle. In order to get one of your men out onto the board, you had to pop a 6. And I'd like you to think about that event, pop until you get a 6. First off, I want to know, does it fit the 5 criteria needed to call it binomial? Because if it does, we already know all about that. Does it have 2 outcomes? Well, yeah, you either get a 6 or not, right? So that is 2 outcomes. Do we know a probability for each? Yeah, we do. Your chance of getting a 6 is 1/6, and your chance of not getting a 6 would be the other 5/6 of the time. Are the pops independent? Sure. It doesn't matter what I get this time. That's not going to affect what I get next time. Here's where things start going south, though. A fixed number of trials? We got to keep going until we get a 6. And that means that we're not having a fixed number of trials, and the binomial falls apart right there. This kind of situation where you are waiting for the first success, that's called a geometric or a wait time model or distribution. Right? Wait time for the obvious reasons. You're waiting for that first success. Logically, there can only be one success, so every other trial must have been a failure. That means the probability that the first success occurs on the nth trial would look like this. One success that has a p probability of happening times failure every other time. So if you think about that, I get one success, but every trial before that, so on the n-1 trials, I had a fail. That's a very easy formula to use. The mean for a geometric distribution is 1 over probability, and if you think about that, it makes sense as well. If there is a 1 in 6 chance that you'll shake a 6, then it'll take you around 6 rolls to get that to happen. The standard deviation for this distribution also has a simple formula, and that is the square root of p divided by q. So we'll keep that in mind. Let's see if we can apply the geometric formula a little bit. We want to find the probability that you roll doubles on your first attempt, or on your second attempt. So on your second try. Now, the way I think about this, I know I wrote the formula with the success coming first, but it really makes more sense when you're using it to think, okay, I didn't get it the first time. I needed to go on to the second. So my fail probability happened first, and then after that I got success the next time. Independent trials, so we multiply, and our probability of getting doubles on our second try is 5/36. The probability that it takes you 4 tries, well, you can figure that very easily. If you are not getting doubles until the 4th time, then 5, 6, you must have failed 3 times. 5, 6, 3 times, because 3 failures, times finally that 1/6. Where we got the success. That's 125 over 6 to the 4th power, and I don't know 6 to the 4th power, so I'm going to leave it just like that. The probability that it takes you at most 3 tries. Okay, you got to be just a little careful here. This is not binomial, so you can't ever get it on the 0th try. That wouldn't make sense. You have to try at least once. So the probability that you get it on the first time, at most 3. So, yep. We're still going because we haven't hit 3 yet. Do we count the 3rd one? Yes, because this says at the very most 3 attempts, so we do want to count the 3rd one. And if you think about the probabilities there, your chance of getting success the first try is 1/6. Your chance of getting success on the second try means you had to have a fail and you had to have a success. And then your probability of getting it on the 3rd try, well, that would be 5/6 twice, because you failed twice, and then get it the 3rd time through. As far as adding those things, folks, we'd need a common denominator that is 6 to the third, or 216. 6 goes into 216 36 times. So this fraction 1/6 is the same thing as 36 2/16, just doing the fraction arithmetic. Here the denominator is 36, and that goes into 216 6 times. So we need 6 times 5, or 30, for that middle fraction. And this one was already over the denominator 216, so that's 25. If we add up all of those pieces, I'm thinking that is 91 over 216, and that is our probability that it takes at most 3 tries to get doubles. So that's a little bit about how the geometric distribution works. We're going to work some problems that concern that tomorrow. I hope that you'll get out there and try that U-Try soon as possible. Bye-bye.